All right, so we want to look at areas of triangles and quadrilaterals. You've been dealing with area for several years, going back to elementary school, so I don't need to spend too much time introducing the concept. It's really just using formulas and understanding that it's space inside a figure. So, the first two formulas you learned were the area of a rectangle and the area of a triangle. Now, the area of a rectangle is typically described as length times width. But this can also be stated equivalently as base times height. When you learn about these formulas, rectangles, squares, parallelograms, each one is described with its own formula, but really they're all base times height. So that's what I'm going to be focusing on, is base times height. Now, if you consider a triangle instead, well, you can show that any triangle's area is half the area of some rectangle. So rather than base times height, I will get 1/2 base times height. Now, it's very important that when we're talking about this, you understand for this and for all of geometry, really, if I say base and height, these must be two measurements that are at right angles to each other. They must be perpendicular. So you notice here, base and height. With the length and width of a rectangle, well, since a rectangle has 4 right angles, those are at right angles to each other. So, let's use these formulas. Base times height, 1/2 base times height for triangles. Again, base and height must be perpendicular. Let's find the area of this triangle. So this triangle right here, I've shown you the lengths of the sides. I'll go ahead and better indicate that 19 is the length of this entire segment. And I know that the area of a triangle is 1/2 base times height. All right, so which segments are perpendicular? Which segments are at right angles to each other? Well, not 15.2, 20.5, I can't use that. The two which are at right angles to each other are this 19 and this segment here, called an altitude. So those are the two that I have to use as my base and height. So the area is 1/2 19 times 13.8. So you're going to go ahead, presumably you're going to use a calculator to multiply this. 1/2 of 19 times 13.8. So you can go to your calculator and you can type this in just straight away. 1/2, I'll put that in parentheses, close them, times 19 times 13.8. And what I get is 131.1. Now eventually we will be doing this with units, so these would be like 19 inches and 20.5 inches and so on. So then my area would be inches squared. As it stands, I just have some general units, so these are units squared, and I can write that. But all I'm trying to focus on right now is that you can actually compute the area correctly. So this is 131.1 square units. Let's move down to this triangle right here. Now again, you can see I've given you the 3 sides of this triangle, 18.8, 15, 28.6. And what I can see out here is this other segment, which is 17 units long. This segment is outside the triangle. Well, I'm asked to find the area of the triangle. This right here is the triangle. Over there, that's not the triangle. But here's the thing. The area of a triangle is 1/2 base times height. Base and height must be measured perpendicular to each other. So I clearly can't use 15 and 18.8 or 18.8 and 28.6 or 28.6 and 15 because none of those angles are right. If I had a right triangle, then I could just multiply 2 of the sides to get the area. As it is, I don't have that. What I can see here is this segment over here, this altitude 17, is perpendicular to this extension of this side. So 15 is going to be my base. 17 is going to be my height. Again, base and height must be perpendicular. A little bit strange in this case because the base and height are perpendicular, but more accurately speaking, the height is perpendicular to a line which includes that base. Either way, I will have 1/2, the base is 15, height is 17. 15 times 17 is 255. 1/2 of 255 is 122.5. And there I have the area of this triangle. Go ahead and move on to rectangles. This rectangle, I've given you the length and width, the two side measures, so I can go ahead and use either length times width, or equivalently, like I said, it is just base times height. Well, the base is 21, the height is 7. If I multiply the two of those, what I will get is 147. So the area of this rectangle is 147 square units. Nothing more to it. Now, I can make this more complicated. I can require you to work a little bit more, give you something a bit more challenging, if you will. Right here, I've told you it's a rectangle. I can see that one side is 10 and the diagonal is 26, which means the other diagonal is also 26 because rectangles have congruent diagonals. But what we know about rectangles is I have 4 right angles. In particular, this is a right angle. Now, if I have a right angle there, that means that I can do Pythagorean theorem to determine this unknown side length. That's precisely what I need to do so that I can actually determine the area. 10 squared, plus I've called it b squared, is equal to 26 squared. Excuse me. 100 plus b squared is equal to 676, which means b squared is 576. So then what I'm going to do is square root 576. Now I know we focus on simplifying radicals a lot, but don't forget, if a number is sufficiently large, you probably want to go ahead and check and see if it's a perfect square or not. So, the square root of 576. Second, square root 576, and it is 24. So that means b is just 24 units long. So then when I want the area is base times height, which will be 10 times 24, or 24 times 10, doesn't matter. Multiplication is commutative. 10 times 24 is 240 units. And you're done. I have the area of this rectangle. It's 240 square units. All right. Let's talk about a couple more formulas. The area of a square is frequently given as s squared. Area is equal to s squared. The area of a parallelogram is base times height. Again, these are really all the same formula. S squared, well, if both of the sides have the same length, this is really just length times width, which is, again, just the same as base times height. Again, though, we must remind ourselves that whenever we're doing this, base and height are perpendicular. So this square, the side is 14, so is this side. If it's a square, all the sides are congruent, all of the angles are right. So when I want its area, whether you think of it as 14 squared or 14 times 14 for base times height or length times width, it doesn't matter. 14 times 14 is 196. And you're done. Okay. The parallelogram. The area of a parallelogram, again, is base times height. So when I'm doing this, I need the base's length, I need the height of the parallelogram. Since base and height must be perpendicular, I look for something that's perpendicular. 9.5 is perpendicular to this side, which means I must use 23 as my base and 9.5 as my height. 15, I cannot use it as either my base or height because I don't have a perpendicular segment to go with it to compute this correctly. I have to use 23 as the base, 9.5 as the height, because those are at right angles. So if I do this, 23 times 9.5, 23 times 9.5 should be 218.5, I think. Yeah, 218.5, right there. That's the area of this parallelogram. All right, last parallelogram. After this, we'll move on from parallelograms, not quite entirely, but we will look at the area of a trapezoid and a formula for the area of a kite and a rhombus. So right here, I've told you again this is a parallelogram. I can see this side up here is 24, this right here is 13, and this portion of this side right here is 19. Well, if this is 24, so is this. This is 19, so this is 5. Why does that help me? Well, again, the area of a parallelogram is base times height. I can see the base is 24. The height is whatever the length of this segment is. But I don't know the length of that segment, so I have to find it. So what I will do is use Pythagorean theorem. So this is h. So what I can do here is say, okay, 5 squared plus h squared is equal to 13 squared. Now if you go ahead and solve this, you might recognize this as a Pythagorean triple, but what you will get is that h squared is 144 and h is in fact 12. I will leave that to you because it's, again, just a simple application of the Pythagorean theorem. So then, if h is 12, then my base is 24 because I used the entire segment times the height, which is 12, and the product of 24 and 12 is 288. So at this point, we've talked about how to find the area of a rectangle, of a triangle, a square, a parallelogram. We've looked at some trickier examples where I either had to do some work to determine a height or a side in order to accurately find the area. And we've even talked about some trickier problems with a triangle where what is the height of that triangle? That's something you have to actually think about. All right. Again, these should all be pretty familiar. This next one, probably not so much. The area of a trapezoid is given as 1/2 the height times the sum of the bases. This can also be thought of, I know typically how I think of it since I have to memorize these, is the average of the bases times the height. If you think about it right here, if I move the 2 over there, then I get the average of the bases, base 1 plus base 2 over 2 times the height. Either way, you'll have the formula sheet in front of you when you're doing this, I would assume. So, the bases of a trapezoid refer to its 2 parallel sides. So right here, this is a pretty simple trapezoid. I can see here that this segment, which is 9 units long, is perpendicular to this segment and to this segment. Now, if it's perpendicular to both segments, that is enough to prove that those segments are parallel. So, the area of the trapezoid then, 1/2 h times the sum of the bases. Nothing complicated here. I just have to understand this formula and be able to substitute in accurately. The height is 9. The bases are 14 and 24. So 1/2 of 9 times 38. And again, you can go to a calculator and multiply this all together at once. If you're doing it by hand, the easiest thing, 1/2 of 38 is 19. And 9 times 19 is 171 square units. So I'm done. That's the area of a trapezoid. I could do more examples, but really it's just the same thing. And of course there are ways to make it more complicated, but I'm focused really on the basic cases of this. All right. So when you're doing these, we've talked about rectangles, squares, parallelograms. Those are all approximately the same formula, though stated slightly differently. We've talked about the area of a triangle, and now we've talked about the area of a trapezoid. All of those will be on the formula sheet if you are using it. The next formula you must have memorized. It is not on any formula sheet that you would be using. A rhombus and kite. What these two shapes share is that they have perpendicular diagonals. As such, there's an area formula that you can use, which is the area of a kite or rhombus is 1/2 the product of the diagonals, d1 times d2. Again, pretty straightforward so long as you understand what these things mean. Like any formula, a formula sheet helps, but you do still have to have understanding of what that formula actually means. So let's look at a couple easy cases. I can see right here, all 4 sides are congruent, which means this is necessarily a rhombus. And if it's a rhombus, it's a parallelogram, which means the diagonals bisect each other, which means not only are these both 11, these two segments right here are both 6. So the formula that I can use is that the area is 1/2 the product of the diagonals. Well, how long are the diagonals? One diagonal has parts that are 6 and 6, so its total length is 12. The other diagonal has parts that are 11 and 11. Its total length then is 22. So, when you are multiplying all of this together, 1/2 times 12 times 22, again, multiply this however you choose. If I'm doing it mentally, the easiest thing, half of 22 is 11, so this is 12 times 11, which is 132. So the area of this rhombus is 132 square units. Now, you might be thinking to yourself, wait a minute, a rhombus is a parallelogram. Why couldn't I just use base times height? You could if you had that information. What I'm showing you here is, again, how this formula works. This formula works for a kite, works for a rhombus, 1/2 the product of the diagonals. So since I can see the diagonals right there, 6, this is also 6, these are both 11. I just went ahead and substituted. 1/2 12 times 22, which comes out to 132 square units. Over here, this is a kite. Now, I didn't tell you it was a kite. I probably would on a test or something like that. But you can determine that it is actually a kite, because I can see, since these are both 5 and that's a right angle, these two triangles would be congruent. Their hypotenuses would be equal. Down here, if that's 3 and that's 5, again, these two segments would be equal, which means if these are congruent and these are congruent, that's what makes it a kite. So, it's a kite. Area is 1/2 D1 times D2. How long is each diagonal? Just take them. This one right here, 5 and 5, that's 10. 3 and 12, that's 15. 1/2 of 10 times 15 is 75. So the area of this kite is 75 square units. And I'm done. That's the area of this kite. Now, rhombuses and kites, as I said, the reason this formula works, 1/2 the product of the diagonals, is because the diagonals are perpendicular. And again, if they're perpendicular, I can make this more challenging by requiring you to do Pythagorean theorem to actually find the length of one diagonal or a part of a diagonal. So let's go ahead and take a look at some examples like that. In this example right here, I can see that it's a rhombus. Each side is the square root of 74. I can see that one diagonal is 14 units long. What I need to know is how long is the other diagonal. What I'm going to do is draw it in to start off with. Now, if this was 14, that means these are 7 and 7. And again, this is a right angle right here. So then the question is, how do I find the lengths of each of these segments? And the answer is with, of course, Pythagorean theorem. So you can call that x or b or really any variable, it doesn't matter. 7 squared plus x squared is equal to the square root of 74 squared. 7 squared is 49. The square root of 74 squared is 74. If I do the subtraction here, 74 minus 49 is 25, which then means, of course, that x is the square root of that, which is 5. So what I now know is that these are 5 units long. Well, at that point, I'm ready. I can find the area. The area is 1/2 diagonal 1 times diagonal 2. One of the diagonals, the one that I started with, was 14 units long. The one that I just found, 5 and 5, that's 10 units. So if I go ahead and do this, 1/2 of 14 times 10 is 7 times 10 is 70 units. and I have its area, 70 square units. I apologize, I said units rather than square units. Please be careful of that in the future. All right, one more. What if I have a kite? All right, in the kite, again, I know that the area of a kite is 1/2 the product of its diagonals. But I know very little about this kite's diagonals. All I've told you is that this portion of this longer diagonal is 3 units long. Now I do know the side lengths. I can see this is 17 units, this is 17 units, this is the square root of 73, so is this, which again indicates that it's a kite. Let's go ahead. What we have to do here is use Pythagorean theorem to find first the length of this part of the diagonal. And then once I have that, I'll be able to come into this triangle and say, okay, Pythagorean theorem again will allow me to find this portion of the diagonal. So I'm going to grab a finer pen so I can work a little bit more clearly. When I'm doing this, we'll call this x. X squared plus 3 squared is equal to the square root of 73 squared. Now, of course, I didn't just come up with the square root of 73 out of nowhere. I picked it because it helps this work. It makes this work out nicely. So x squared plus 9 is equal to 73, which means x squared is 64, which means this segment must be 8. Now again, it's a kite. These are congruent. These are congruent. Not only is this 8, this segment down here is also 8. Alright, so I'm halfway there. I found this 8, now I need to figure out how long this segment is. So I'll go ahead and call that y. So then what I can see is 8 squared plus y squared should be equal to 17 squared. (64 plus y squared is equal to 289, which means y squared is 225. And if you go ahead and square root that, the square root of 225 is 15 exactly. Alright, so now this is 15. Now what I have to do then is go to my area formula. The area is 1/2 the product of the diagonals. So that's 1/2. One diagonal, 8 and 8, is 16 units long. The other diagonal, 3 and 15, is 18 units long. So 16 times 18 is 288. Half of 288 is 144. So the area of this kite is 144 square units. There's nothing more to this problem, nothing less. This is easily the hardest of the problems I've just done, but again, it's really just a simple application. Multiple applications, though, of Pythagorean theorem. So again, this all goes to understanding where the right angles are in these figures and how you can use those, because we've seen that's the principal way of making these a bit more challenging. And again, whenever you're doing these, didn't come up here, but to reiterate, whenever you hear base times height, base and height are perpendicular. Area could get much more complicated, but it's not a topic that we're going to go in that direction with. We need to memorize these formulas. You need to master these formulas. The one you really need to memorize is, again, the one we've just been using, the area of a rhombus and kite, which is 1/2 the product of the diagonals. I hope this has been helpful. Thank you.